Hello! Thanks for joining us today. We are looking for a Flutter developer to join our team, and based on your background, it looks like you have a couple of years of solid experience. To start things off, why don't we dive right in with some of the basics to get a feel for your approach? Could you explain the fundamental difference between a stateless widget and a stateful widget?
Sure. The fundamental difference really comes down to whether the widget needs to change its appearance or the data it displays after it has been initially built. A stateless widget is immutable. This means once it is created, it cannot change its internal state. If you need the screen to update, you have to create a completely new instance of that widget. On the other hand, a stateful widget has a separate state object. This allows it to track data changes over time. When that data changes, you can call the setState method, which essentially signals to Flutter that it needs to redraw the widget with the new information. The key is that it does this without needing to recreate the entire page or the entire widget hierarchy from scratch.
That makes sense. Since you mentioned setState, let's expand on that. In a real-world project, as the app grows, you usually hit a wall with just using setState. Can you explain the difference between using setState and a dedicated state management solution like Provider or RiverPod?
Definitely. setState is great for local state management. If you have a simple toggle switch or a counter on a single screen, it is the most efficient tool because it is built-in and simple. However, as the app grows, you run into a problem called prop drilling. That is where you have to pass data through 5 or 6 layers of widgets just to get a piece of information to a child widget that actually needs it. CANDATE. Dedicated state management tools like Provider or RiverPod solve this by separating the business logic from the user interface. Instead of passing data through constructors, any widget in the app can access and update the state directly. This is much more performant because you can target specific widgets to rebuild. Instead of rebuilding an entire widget tree, only the small parts that actually depend on that specific piece of data are redrawn. It makes the code cleaner and significantly easier to test and maintain.
Speaking of the widget tree, for someone who might be newer to the framework, how would you describe the core concept of the Flutter widget tree?
The core concept is essentially that everything in a Flutter UI is a widget. Whether it is a layout element, a piece of text, or even the padding around a button, it is all a widget. These are organized in a parent-child hierarchy. You start with a single root widget, which contains other widgets, which in turn contain more widgets. This tree structure allows the parent to manage the layout and configuration of its children. When the state changes, Flutter updates this tree. Because it is designed to be very efficient, it only redraws the parts of the UI that actually need to change, which is why the app feels smooth and responsive even with complex layouts.
Now, let's talk about the internals. I want to understand how you view the actual rendering process. Could you give me a conceptual walkthrough of how Flutter turns your Dart code into pixels on the screen?
Right, so Flutter uses a layered pipeline. It starts with the widget tree, which is really just a set of lightweight configuration blueprints. These blueprints are used to build and update the element tree. I like to think of the element tree as the manager. It keeps track of where each widget sits in the hierarchy and manages the lifecycle of the widget. From the element tree, we get to the RenderObject tree. The RenderObjects are the heavy lifters. They are the ones that actually calculate the size of a widget and its exact position on the screen through the layout process. Once that layout is settled, Flutter enters the painting phase. The RenderObjects record drawing commands, and these commands are sent to the engine, either Impeller or Skia. The engine then converts those commands into GPU instructions to actually paint the pixels on the hardware screen.
You mentioned the rendering pipeline. Could you elaborate on why that specific architecture allows Flutter to achieve such high performance compared to some other frameworks?
The main reason is that Flutter does not use native OEM widgets. In other frameworks, there is often a bridge where the framework has to tell the native platform, like Android or iOS, to create a native button or a native text field. That communication can be expensive and slow. Flutter bypasses that entirely. It uses its own rendering engine to draw everything directly onto a canvas. By controlling every single pixel and not relying on the platform's native UI components, Flutter avoids that expensive bridge. This allows it to maintain a consistent 60 or 120 frames per second, because the path from the code to the GPU is much shorter and more direct.
That's a great explanation. Let's shift gears to a bit of a more practical scenario. Imagine you are building a feature where you need a very specific UI element, like a complex graph or a custom geometric shape that doesn't fit into a rectangle. When would you decide to use a custom painter versus just nesting standard layout widgets?
Standard layout widgets like row, column, and stack are fantastic for the typical box model, rectangles, and linear alignments. But they fall short when you need shapes that can't be achieved by nesting boxes. If the design requires custom geometric paths, complex curves, or radial gradients that follow a specific non-standard shape, standard widgets become impractical or even impossible. For example, if I need to draw a fluid animation where a line connects two moving points based on precise mathematical coordinates, I would use CustomPaint. It allows me to define exactly how to draw on the canvas.
In that same context, from a performance perspective, is there a point where Custom Painter is actually more efficient than using built-in widgets?
Yes, absolutely. If you need to render a large number of dynamic elements that change frequently, Custom Painter is significantly more efficient. Every standard widget is an object in a tree. If you have hundreds of them, you're creating a massive amount of overhead because each widget requires its own state and layout calculations. With a Custom Painter, you bypass the widget tree entirely and draw directly onto the canvas. You are executing drawing commands in a single pass. This reduces memory usage and prevents frame drops during animations because Flutter isn't managing a massive hierarchy of objects. It's just executing a set of painting instructions.
Let's talk about the lifecycle of a widget. If you are working with a stateful widget, can you walk me through the lifecycle of its state object?
Sure. The lifecycle begins when the widget is first inserted into the tree, which triggers the createState method. Immediately after that, initState is called. This is where I usually initialize data, start listeners, or set up controllers, and it only runs once. Then we have the build method, which is called every time the UI needs to be rendered, like after a setState call. If the widget's configuration changes because the parent updated, didUpdateWidget runs, which allows the state to react to those new configuration changes. If the widget is temporarily removed, it can be deactivated. Finally, when the widget is permanently removed from the tree, the dispose method is called. This is a critical step because it's where I clean up resources, like canceling timers or closing controllers, to prevent memory leaks.
Let's move into some more advanced territory. In a mobile app, you often have to deal with heavy computations. Since Flutter is single-threaded on the UI thread, how do you handle thread concurrency or heavy background tasks to keep the UI from freezing?
Since everything runs on the main UI thread, any CPU-intensive task will cause jank or a total freeze. To prevent this, I use isolates. The interesting thing about isolates in Dart is that they don't share memory. This means we don't have to worry about the typical locking issues or race conditions you see in other languages. They communicate by passing messages. For simple asynchronous things, like fetching data from an API or reading a file, I just use future or stream. But if I'm doing something heavy, like parsing a massive JSON file or performing image processing, I must spawn a separate isolate. The most convenient way to do this is using the compute function. It handles the creation of the isolate, runs the task, and returns the result back to the main thread automatically, which keeps the UI perfectly responsive.
That leads perfectly into a specific scenario. Suppose your app needs to read a camera feed, and process those frames in real time. What packages would you use, and what architectural considerations would be most important here?
For the camera stream, I'd use the camera package. For the actual analysis, depending on the goal, I'd use something like Google ML Kit or T-Flight Flutter. The biggest architectural concern is avoiding UI jank. Processing image frames is incredibly expensive. If I tried to do that on the main isolate, the app would freeze. I would have to offload the image analysis to a separate isolate using a long-lived worker isolate or the compute function. Another critical point is managing the image stream. Cameras produce frames faster than a CPU can often process them. If I try to process every single frame, I'll create a memory backlog, and the app will eventually crash. I would implement a mechanism to skip frames if the processor is still busy with the previous one, ensuring the app stays stable.
Let's talk about the overall structure of an app. You mentioned separation of concerns earlier. What does that actually look like in a Flutter project?
Separation of concerns is all about dividing the program into distinct sections so that each one has a single responsibility. In Flutter, I divide it into three main layers: the UI layer, the business logic layer, and the data layer. The UI layer should only care about how things look. It shouldn't know where the data comes from, it just knows how to display it. The business logic layer handles how the app behaves, and the data layer manages the actual fetching and storing of information. For example, if I'm handling a user profile, my data layer would have a class to fetch the JSON from an API. My logic layer would then process that data into a model. The UI just listens to that model. The beauty of this is that if we decided to switch our database from a local SQLite file to a cloud API, I would only have to change the code in the data layer. The UI and business logic wouldn't even know a change happened.
How do you typically handle those API calls and JSON serialization to keep things clean and type-safe?
I avoid manual mapping of maps to objects because it's error-prone and tedious. Instead, I use model classes with factory constructors. For larger projects, I prefer using code generation tools like JSON Serializable and BuildRunner. This ensures that the parsing is type-safe and consistent across the whole app. For the networking itself, I usually use the DIO package because it offers more flexibility than the standard HTTP package, like interceptors and better error handling. The flow is usually that a controller or provider triggers the API call, and then it updates the UI state to reflect whether the request is currently loading, successful, or has failed.
Speaking of failure, how do you handle network errors gracefully so the user doesn't just see a spinning loader forever or a crash?
I always wrap API calls in try-catch blocks to prevent crashes. I specifically look for different types of exceptions. For instance, a socket exception usually means there is no internet connection, while a timeout exception suggests the server is struggling. Instead of showing the user a technical error like socket exception, connection failed, I map those to user-friendly messages, such as please check your internet connection and try again. In the UI, I use my state management to switch views. The user sees a loading state, and if an error occurs, they see a clear error screen with a retry button. This is much better than a blank page or a frozen app.
I want to touch on a specific architectural pattern. Can you explain the concept of lifting state up?
Lifting state up is used when two or more sibling widgets need to share the same data. Since state in Flutter typically flows downwards from parent to child, two siblings can't talk to each other directly. To solve this, I move the state from the child widgets up to their closest common ancestor. The parent now manages the data and passes it down to the children as read-only arguments. If a child needs to change that data, the parent also passes down a callback function. The child triggers the callback, the parent updates the state using setState or a provider, and then the updated data flows back down to both children.
What about when you need to go beyond the Flutter framework? Tell me about custom platform channels. When do you have to use them?
Platform channels are the bridge that allows Flutter to communicate with the native host platform, like Android or iOS, using asynchronous messages. Flutter is powerful, but it runs in its own engine and can't directly access every single native API. If I need a feature that isn't provided by an existing plugin, say, a very specific hardware sensor or a deep OS-level setting, I have to create a platform channel. I write a method channel in Dart to send a request, and then I write the corresponding native code in Kotlin for Android or Swift for iOS to execute the action and send the result back to Dart.
Let's go back to animations for a moment. If you were asked to implement a custom fade or slide animation, how would you approach that?
For custom animations, I generally use an animation controller and a tween. The animation controller is what manages the timing, the duration, and whether the animation should repeat. The tween is used to define the start and end values. For example, for a fade, the tween would go from 0 to 1 for the opacity. I would then wrap the widget in an animated builder, or use specific transition widgets like fade transition or slide transition. This tells Flutter to rebuild the UI as the animation value changes. Now, if the animation is simple, I wouldn't go through all that boilerplate. I would use implicit animation widgets like animated opacity or animated positioned. With those, you don't need a controller. You just change a value and call setState, and Flutter handles the interpolation and timing internally.
We've talked a lot about performance and rendering. If you were handed a Flutter app that was stuttering, what we call jank, how would you go about identifying and addressing those bottlenecks?
First, I'd start with the DevTools performance overlay. I want to see if the app is missing frames and whether the bottleneck is on the UI thread or the raster thread. Once I have a general idea, I'd use the Flutter inspector to look for unnecessary widget rebuilds. It's common to find that a large part of the tree is rebuilding when only one tiny piece of data changed. I'd also use the CPU profiler to find any expensive functions that are blocking the main thread. To fix these, I'd apply a few strategies. I'd use const constructors wherever possible to prevent unnecessary rebuilds. I'd move any heavy computation to an isolate. And if there is a specific area of the screen that updates frequently while the rest stays static, I'd wrap that area in a repaint boundary. This prevents Flutter from redrawing the entire screen when only one small part changes.
That's a very comprehensive approach. Just to wrap up on the technical side, if you had to explain the purpose of the build method to a junior developer, how would you describe it?
I tell them that the build method is essentially the blueprint of the widget. Its entire purpose is to describe what the user interface should look like at any given moment. Every time the widget needs to be displayed or updated, Flutter calls this method to figure out which widgets, like text, images, or buttons, should be on the screen. It returns a widget tree, which the framework then turns into pixels.
Everything you've described sounds very solid. You have a good grasp of both the high-level architecture and the lower-level rendering engine. Before we finish, do you have any questions for us about the team or the projects you'd be working on?
I do. I'm curious about the current state of your codebase. Are you mostly using a single state management solution, or is it a mix? Also, are you currently using the Impeller engine for your iOS builds, or are you still seeing issues that require sticking with Skia?
Those are great questions. We've standardized on RiverPod for state management to keep things predictable, and we've actually fully transitioned to Impeller for iOS, which has solved a lot of the shader compilation jank we were seeing. We can definitely dive deeper into that during the onboarding. It was a pleasure talking with you today. We'll be in touch very soon.
Thank you. I appreciate the time and look forward to hearing from you.